continue our afternoon session with Hülya Argüz from University of Georgia. Hülya.
Thank you very much for the invitation. It's a great pleasure to be here. So my plan today is to tell you about the KSP modularized space of local ideal surfaces. Here's my concrete plan. So I will very shortly recall what a modularized space of stable curves is. The KSPA modularized space will just be a higher dimensional generalization of it. And I will tell you what the Hacking-Hülya conjecture, which is now our theorem, that Alexiev and Buzet is saying. So this is the main theorem of the talk. The KSP modularized space of stable local ideal surfaces up to passing to a finite color is a toric variety. And I will tell you motivation for this, how this story is related to mirror symmetry. It will be a crucial ingredient in the proof. And I will tell you how the proof works, which involves a mirror construction, which we call semi-stable mirrors, for maximal degenerations of polarized local ideal surfaces. And it also involves using analyzing intrinsic mirrors to grow a seabed of these semi-stable mirrors that we construct. So I will tell you details of this. Okay, to start with, if you look at the Deligne-Mumford modularized space of curves and whose points are given by genus G stable curves with unmarked points, CP1 to Pn, where C is a reduced curve with arithmetic genus G, which has at first nodal singularities, and P1 to Pn are distinct smooth points. And you're additionally having a stability condition, assuming that the automorphism group of C together with these points is finite, which is equivalent to saying the canonical divisor, the sum of the canonical divisor with the divisor given by the sum of these PIs is ample. And this modularized space is extensively studied. It is known that this M bar Gn is a proper Deligne-Mumford stack of dimension 3G minus 3 plus n. And there has been also several generalizations of this modularized space. One of them studied by Hasse, known as moduli space of weighted stable curves. In this setup, one considers not only points P1 to Pn, but in addition to each point, one associates a weight. So the points of this moduli space of weighted stable curves consist of genus G stable curves with n marked points P1 to Pn. As before, they are ordered in smooth marked points, but unlike before, they are not necessarily distinct. So different points can come together as long as the associated weights sum up to less than or equal to 1. And to each point associated weight, I denote by epsilon I associated to pi is some number between 0 and 1. And here, the analogous stability condition, similarly as before, reads that the divisor given by the canonical divisor plus the sum of the weighted points this time should be ample. Historically, actually, these kind of moduli spaces, some simple cases, or in some versions of these moduli spaces, were studied much before than Hasse. They were introduced, they are known as Lozève-Manin spaces. So Lozève-Manin studied the particular case where they consider genus 0 and they take n plus 2 ordered marked points. I try to illustrate here on a curve where you can imagine P0 and P infinity, your 2 points on P1 giving the anti-canonical divisor. And in addition, you consider n more points on the curve. And to P0 and to P infinity, you're associating weights 1, and to all other points, you're associating weight epsilon, where epsilon is a very small number close to 0. And these spaces were studied by Lozève-Manin, who showed that this moduli space is a toric variety. And they described the polytope for this toric variety, which is a parameter hedra and so on. And the KSP moduli space will actually flavor, if you just do KSP in the one-dimensional situation, be very similar to the Slozif-Manin moduli space. It's also going to be a toric variety. So if you look at the KSP moduli space in this situation, if you look at only dimension 1 of P1, if you look at this divisor given by the anticanonical divisor P0 plus P infinity and the endpoints, which I denote the sum of these endpoints by C, then the KSP moduli space is a moduli space of such curves where there's just some set difference, you don't consider ordered but non-ordered points, and then you just divide by Sn, which is a symmetry group, and this moduli space I will explain in more detail and more examples has been studied in the toric case by Valery Alexiev, and it is known that this moduli space is again a toric variety. And the fun for this toric variety is going to be the secondary fun associated to this interval, which is divided into n intervals. So the secondary fun already appeared in the talks of Hiroshi, and I will tell you more about this once I come to more examples. So generally, KSP moduli space is something that works in higher dimensions. It's a higher dimensional generalization of this idea of moduli space of curves. So when in the KSP moduli space, we look at stable pairs YB, where Y is a projective variety and B is a Q divisor, such that YB has SLC singularities, which are appearing in the minimal model program. These are, you can think of them just as higher dimensional analogs of what is a nodal singularity on a curve. And ky plus b is Q Cartier, and ample is the analogous stability condition in this setup. And we denote by MKSP the moduli space of stable pairs, and its connected components are known to be proper Deligne-Mumford stacks. Unlike in the situation of curves, they are not generally irreducible, and people studying KSP moduli spaces usually try to describe how the specific components, what are the specific irreducible components of this KSP moduli space. As an example, if you take YD to be a toric pair by a toric variety, D its toric divisor, and L an ample line bundle on it, you can consider MYDL, the closure in the KSP moduli space, the locus of stable pairs, Y, D plus epsilon C, where C is inside the linear system of L. So C corresponds to a divisor in the linear system of L. And one of the key results of Valery, dating back to beginning 2000, says that for a toric pair with an ample line bundle, the KSP moduli space, the normalization of the KSP moduli space MYDL, is a toric variety with associated fun given by the secondary fun for the momentum prototype of YDL. And he studied also geometrically, concretely, the KSP moduli spaces of abelian varieties, and apart from that, not a lot has been done. And what we did is to study the KSP moduli space of polarized Laplacian surfaces. So what is this? So we fix a polarized Laplacian surface YDL, where Y is a projective surface, D is a maximal reduced anticanonical divisor in Y, and we assume YD has low canonical singularities. So in the simple situation, Y could be smooth and D could be normal crossing. This is a particular example, but our definition of low Calabi-Yau does not impose Y to be smooth. So we impose Y to have we allow Y to have low canonical singularities. Maximal reduced anticanonical divisor. So we're assuming D to have at least one singular point. So we don't want D to be smooth. like it's one of the standard assumptions in the gross Seabird program. If you assume D to have at least one singular point, its tropicalization is going to have the correct dimension and so on. So we don't want, for instance, P2 with the smooth elliptic curve, but we want at least one node and so on. And MYDL, if you look at the closure in the KSP moduli space of the locus of stable pairs, which are deformation equivalent to the stable pairs YD plus epsilon C, where C is in the linear system of L. So in the purely toric situation, there is no complex modular space of it. The toric varieties are rigid. But here, we look at deformation equivalent stable pairs equivalent to deformation equivalent to YD plus epsilon C, where we also vary C. And we try to understand what this modular space is concretely geometrically. Here I drew a picture to illustrate what elements, if assuming that Y is smooth, I just drew some D in black. So the stability condition amounts to saying ky plus d plus epsilon c should be ample, but because d is anti-canonical, ky plus d is 0. So epsilon c is automatically ample. The stability condition for such pairs automatically holds. And if you translate what the C condition should mean, it means that your pair C in your surface Y should not go through the zero-dimensional strata of your divisor D. So we are looking at the modular space of such pairs. And our main result that I will go through its proof shows that this modular space up to a finite curve is a toric variety. This was a conjecture of Hülya and Yu, dating back to a couple of years ago. And for toric varieties, it was the result in the purely toric situation, it was the result of Valerie that I mentioned. And so far, the only known cases for which this conjecture was proved was due to Hülya, which consists of exactly 6 cases. So they proved it for the crystal surfaces of degree n, where n is between 1 and 6, and they fixed C to be a cycle of n minus 1 pairs, and they fixed L to be the anti-canonical bundle over Y. In this situation, this was proven, and we're proving this for all local labial surfaces. And we plan to put our paper on arXiv in a couple of weeks' time, so it should be in February on arXiv. I will tell you how the proof works after I tell you a motivation and why this whole KSP story is related to mirror symmetry. So here is a vague motivation. In the next slides, I will provide a more concrete motivation. So if you look at the MYDL, the MYDL can be realized by its definition as a complex modular space of YDL, which can be taught of a complex modular space of a Calabi-Yau threefold. You can associate to YDL this way. So if you look at the complements U, Y minus C, this is a non-complex Calabi-Yau surface. And if you look at the restriction of your curve C onto U, this is given by the vanishing focus of a section of L restricted to U. I call this section S. Then you can consider this Calabi-Yau threefold, which I call C here, associated to your YDL. And this is the threefold, which is given by the vanishing locus, by the locus UV equals S inside the total space of the bundle, the sum of line bundles L and the trivial line bundle over U. So here I try to draw a picture of U and C inside here. I do the real picture of the curve C. So everywhere apart from C, you have a C star, and everywhere over every point of C, you have this U equals S, where U is a coordinate on L and P is a coordinate on the trivial part. So you can form a threefold like this associated to YDL, and the KSP modular space captures the complex modular space of such threefolds. And then mirror symmetry proposes that this KSP moduli space should be realized as the extended complexified scalar moduli space, what actually appeared quite a lot in Hiroshi's talks. He called this the global scalar moduli space of the mirror to Z. But when I usually talk, I will not say the mirror to Z. Z can be thought of like families of YDL, so I will call it the mirror family to YDL. So the mirror symmetry expectation is to visualize the KSP moduli space as a mirror family to YDL. And again, very vaguely, one should expect to view this scalar moduli space as a toric variety whose sum is the union of scalar or ample cones of the birational models of the mirror family to YDL.
It seems to be a common bond of the number space that to do with the number space common bond.
Yes. Yes, I think so. But that should be true, but I haven't really thought much about this. Do you have any comments? There should be some story like that to view this moduli space. Do you maybe take some suspension?
Well, all I can say is that Valera knows this very well.
Yeah, I'm pretty sure this is Valeri's good point. I believe this should be true. And here I just wrote a very vague motivation. In general, you have a Calabi-Yau here. You don't expect the hierarchical even to be rational in general, but just vague expectations like Kawamata's point conjecture and so on. Proposes this should be true. Okay, so here is a more concrete motivation in the toric situation. So if you consider your Y, the toric variety, given by the product of two copies of P1s, and if you assume your divisor D is minus KY, and if you fix your ample line bundle L also to be minus KY, here I drew P, the momentum polytope associated to this Y. Here I try to explain why the KSP moduli space should have to do with the complex moduli and the generations of YDL. So if you look at the KSP moduli space, you're looking at curve C inside the linear system of this L, which means your curves C are given by the vanishing locus of such an equation whose Newton polytope will give you the P, and there are some coefficients AIs. And then in toric geometry, if you would believe things should be toric, in toric geometry, every point in a toric fan of a toric variety corresponds to the limit of a 1 parameter subtorus 1 parameter family. And studying all such limits will tell you what all points of your fan should be. So if you look at limits of 1 parameter families where you vary these coefficients AIs, and assume in the limiting in the Pauli series as leading term T to HI, say for some height HI an element of C, then you can study all these heights to varying such terms in 1 parameters correspond to, so amounts to studying all such heights. Actually, I don't have A1 to A4 because there's a C star square action on the toric variety. You can reparameterize, you can cut off 2 dimensions. You can scale everything, which amounts to cutting off 1 dimension. So my set of heights are actually not 5, but 5 minus 3. So I have 2 heights in this case. My KSP moduli space is going to be 2-dimensional. In general, the KSP moduli space is always going to be having dimension R to the number of integral points minus the dimension of P minus 1. And if you look at the data of all such heights, which you obtain by varying in a 1 parameter family your curves, this defines a convex piecewise linear function. If you lift all your points to given heights, if you look at the lower convex hull, then you can define a convex PL function whose domains of linearity corresponds to the lower convex hull determines the polyhedral decomposition on P. And so you determine a PL function out of this data. And if you take the limit as t goes to 0, so here I drew the different PL functions, the different domains of linearities of the PL functions, which amounts to subdividing your polytope P. Each of these determine a toric degeneration of your original toric variety. So from the data of this YDL, by taking C's, varying these C's, you actually do determine the generations of YDL, in which, in this case, so the secondary fun, which I drew here, is the fun of P2. Each maximal dimensional cone of the secondary fun corresponds to a subdivision of your original polytope. Okay, so this is an A picture why the KSB moduli space has to do with the secondary fun and the complex moduli of YDL. And here is the motivation on why this should have to do with mirror symmetry. If you look at the mirror of the toric variety YDL, the way to obtain is to put your polytope of YDL at type 1, take the cone of it, and you view now not as the polytope picture of the mirror, but as the fun picture of the mirror. So your mirror to YDL, or your mirror family to YDL, or if you want your mirror to your three-dimensional Z, is going to be the toric variety whose fun is the cone over this polytope. But actually, we don't want to only consider YDL a single YDL. We want to consider YDL together with the maximal degeneration of it to understand maximal degenerations of YDL. In this case, we declare the mirror to be, so if you take this particular maximal degeneration, there's one toric maximal degeneration in this situation. And if you take the cone over this, you get a new refined fun, and this amounts to taking the Crepont resolution of your singular toric variety, whose fun is the one given on the right-hand side. So the mirrors to maximal degenerations of YDL correspond to Crepont resolutions of your singular mirror. And it is known that indeed, if you look at the secondary fun of YDL, this can be recovered by studying the birational geometry of all Crepont resolutions. And the secondary fun is equal to the Mori fun, the secondary fun of YDL with the maximal degeneration is equal to the Mori fun of this Crepont resolution. So here, the Mori fun is the fun whose maximal cells consists of cones, whose maximal cones consists of all the net cones. In this example, I have only one net cone because I have only one toric Crepont resolution. In particular, it has to do in this example, I have only one integral interior point. But in general, there can be many Crepont resolutions. There can be many maximal degenerations. The Mori fun will have as many cones as you have Crepont toric resolutions. And then, in addition, you have some bogus cones, which are less important because they can clearly be determined from the data of all NEF cones if you know all the NEF cones. So in this example, just to explain what these are, you have this maximal degeneration of P. If you forget one of the diagonals this way or this way, forgetting one of the diagonals amounts to having a birational map from x to x prime or x prime, which are the corresponding, which correspond to contracting the P1 plus P1 in one direction or the other direction. And the left comes, so if you do such a birational contraction of P1 plus P1, you, the left cone of x prime as well as x prime are these squares in this case. And the bogus cones are just the cones which whose radiometers are net cones of these, what you, your x prime or x prime and sum together with what you contract. So if you know the data of all net counts, you can recover the data of all bogus counts. So that's why they're called bogus by Shankiel. So the upshot here is if you know all Crepont resolutions and all net counts, you can tell what the secondary fun is. This tells what the KSBA moduli space is. This is in the purely toric situation, and we wanted to do something in a non-toric situation to prove this conjecture. So we generalize these ideas to the non-toric case. So the first problem, if you want to generalize these ideas to the non-toric case, is to find what is the mirror to a given YDL. So if you have a polarized equilibrium surface, the first problem is how can we describe all the singular X bar that I denoted in the previous slides. In this toric case, it was just the singular toric variety whose fun is the fun over the polytope. So now we need to describe X bar and Crepont resolutions and to find mirrors to maximal degenerations of YDL. So just as a note, in the so far known examples for which the conjecture was proven and the 6 subsets of surfaces, where I think you prove this conjecture, things are in some way self-mirror, by which I mean the dimension of the complex modular space equals to the dimension of the killer modular space, so things can be identified. And in all their cases, the mirror X can be taken as K by the canonical bundle over Y, and X bar is obtained by contracting Y to a point. But in general, things are not so nice, symmetric, and we need to describe the mirror. And so far in mirror symmetry, there hasn't been a construction telling what is the mirror to a maximal degeneration of a polarized equilibrium surface. Because so far the available mirror constructions in the setup in the local labial setup work for, like, due to Gross-Seking Kiel, you can construct the mirrors of single YDL or YDL with trivial degenerations. If you do Gross-Seibert, you can construct mirrors to toric degenerations of calabials or localabials or log-smooth, what is so-called log-smooth degenerations. And we are not in the log-smooth situation. Our degenerations will not be log-smooth. And there is the non-Archimedean mirror construction of Kiel-U, which so far works under the assumption that Y minus D should be affine, which is also not the case in our setup. So as it was mentioned by the mirror, I should mention that in the framework of the Gross-Seibert, mirror symmetry, all Gross-Seibert mirror symmetry appears in the first subgroup. So one considers Y so that there would be a degeneration of it, a toric degeneration of it into Y zero. I will draw a very vague picture. And the intersection complex of Y zero, by definition of toric degeneration, the components are toric, they meet along toric strata. So if you have singularities in the intersection complex of Y zero, they're always in the interior of edges in the all Gross-Seibert framework. So this means if you take this combinatorial duality called the joint duality, you will form the intersection complex of your mirror sample pharma, which also always has singularities in the interiors of the edges. So this is the dual intersection complex of your original sample fiber, which is used as the intersection complex of the mirror sample fiber you want to construct, and finally ball crossing and so on to describe what the smooth things should be. And so the mean cross events and the intrinsic mirror symmetry, you can look at log-smooth situations where, in particular, the components need not to be toric, but it's still the zero-dimensional strata. It's a zero-dimensional strata you don't find singularities. So you cannot look at things like, which will appear in our case if you consider maximal degenerations of polarized circular yaws, you will typically end up having singularities in the middle. In this situation, we do not really know how to construct a mirror using the Proceeded framework. However, the log-smooth situation, what we do know is if there would be a mirror, I roughly draw because it's not by the point I will tell you how to define all these complexes, it will be more than a combinatorial duality to explicitly describe these things. So in our generations, the protection complex of Auditorium will typically have similarities at the corners. And the dual intersection complex will typically have similarities only at the interiors of maximal cells. Proceeded does apply to such situations. You can construct a mirror to Xera, which is an intrinsic mirror. So one issue in this new setup, one subtlety in this new setup is that in all procedures you can go both ways. You can take the mirror and the mirror of the mirror and so on. But there was not a possibility to take the intrinsic mirror and not take the mirror of the mirror. And what we do is we describe this. So we will start with maximum.
Modular spaces and low pressures is provided by the modular spaces. And then there are some degeneration. The immune study of maximum degeneration.
We study only log-smooth maximum degenerations. The mirror symmetry construction works only in particular log-smooth degenerations. And so our degenerations are typically not going to be log-smooth. The maximum degenerations are generally polarized areas are not going to be log-smooth.
So the Hülya cubic minus cubic minus cubic will you want to come out of this?
You want a cubic surface? So a maximal degeneration you can obtain it by just triangulating it into triangles of size 1 that I will give an example. And I will give an example why we don't have maximal. In particular, these are not very well-defined functions. What is the intersection complex? What is the dual? So I will explain what are these, how we define these. But in their setup, what they do so far is to assume they are log-smooth, which consequently implies that in the intersection complex you never have a singularity in the vertices. But we will have singularities and vertices for maximal degenerations. I will give a concrete example of a maximal degeneration. Okay, so what we do is to describe these and I will, in 2 slides, give an example of them. In summary, my slides went off. Okay. What we construct is the inverse Proceeded mirror. So we start with one yaw, we start a mirror construction, then we will take the intrinsic mirror of it. And at the end of the day, we will show what we obtain by taking the double mirror against the KSP moduli space. So the first step is to tell what is the mirror. So for some long time, I should say, I was hoping that I can still find a way to do like local resolutions to resolve the non-log-smooth family and still try to do Proceeded mirror symmetry for the resolution. But I'm going to, we don't want the mirror to the resolution, but mirror to your original thing. One needs to still relate the mirror of the resolution, show it extends to the mirror of the original thing. And that's very messy. So we had spent quite some time to show it similar things only for cluster varieties. In general, it's not so easy to extend beyond log-smooth. So here it goes, the first starting point for describing mirrors of non-log-smooth degenerations, maximum degenerations of polarized equilibrial surfaces. So we first use a previous result of Engel Friedman, who says that any equilibrial surface lineal admits a nice storic model, y prime, b prime, y bar, b bar, l bar. Like by toric model, I mean like in the usual, in the 2-dimensional case, you can always find a toric model up to corner blobs. So this is up to corner blobs. where L can be obtained as L bar minus some AI EIs, where AIs are integers. So by my storic model, we particularly mean they describe in their paper, you can obtain the associated signs and polytope to your local labial surface as a polytope which you obtain from a toric polytope of a toric variety. So this is the toric polytope, the 6 to 9 row. And you can obtain your signs and polytope always in a way that you cut out channels in a nice way. By nice way, there's always a central pointation of the toric polytope. So they can join the central point to the vertices, and the triangles you cut off always lie inside these triangles you subdivide, you obtain. And so this is one of the input data for us to describe all these. So this duality is not as simple as just combinatorial discrete duality. We need to use this geometry. And so we start with this nice Samington polytope associated to radial. The first thing we show is that there's a nice triangulation T on the Samington polytope. And so maximal degeneration, whose special fiber is given by P and T. Here are some pictures, so you'll appear in our paper. So the way we drew the triangulation is we join the central point to the tips of the triangles you cut out, and then there's some pulling construction. So we show you can always find some triangulation of your Samington polytope into triangles of size 1, it determines the maximal degeneration whose intersection complex is this. And then our goal to understand the mirror to YDL is to read this as the dual intersection complex of the mirror and construct X0 whose dual intersection complex is given by this PT. And then to smooth X0. Here I will draw easier picture for YDL. Assume your YDL, the Samington polytope is this pink part you cut out triangle of size 2. And here I try to explain how we construct first a normal crossing surface whose dual intersection complex is PT. So first, for every point here, which is not a singular point, which is not, for instance, the tip of what we cut off the whiting, you input an irreducible component of your normal crossing surface that we want to construct given by the toric fan around that point. If you're on the boundary, you will include like non-compact toric varieties. And if you're on the singular point, if you look at the fan around the singular point, we consider an irreducible component of X0, which is the Q branch times smoothing of the toric surface, which we describe using this model. So here, if this is your intersection complex of Y0, you can imagine you can, forgetting what we put out, you can first take the toric combinatorial dual, you will obtain this picture. But for what you cut out, we will push in singularities that the monotony direction will be determined by this geometry. And because we cut out something of size 2 here, it means you can push in singularities first to that corner and then that other corner and go all the way until the interior. So in this example, if you smooth all the corners, so this small triangle was a P2, it will be a P2 with a conic, not 3 lines with a conic interline. By the -2 theorem, the other component will be actually the Hirse group surface F6. So for this example, your central fiber will be the union of P2 and F6 and 2 non-compact toric varieties whose polytopes will be these non-compact parts apart.
How do you see that it's MC?
Because you smooth this corner when you push in the singularities of P2, you get this device in P2, which is a conic, so you get self-intersection 4, and then there's some -2 theorem, and this the total local surfaces. So the self-intersection from the sides and the self-intersection of the device that you see inside there should add up to -2. So because you have 4 here on the other side, you should have -6. So that gives you, we studied the geometry concretely. That gives you the hirsuter surface. And here we do some bit of deformation theory. So locally, these singularities are always Bach singularities. You can always locally smooth down. We do some local to global deformation theories to show we can globally smooth down. There is some technicality to actually smooth down together with the divisor, so the obstruction is slightly subtle to it. But we do some deformation theory to show we can do such smoothings for pairs. And then we construct a normal crossing surface H0 associated to our degeneration, maximal degeneration of IDL. And then the next thing we do is to do log smooth deformation theory to smooth the surface. So we wanted to concretely do log smooth deformation theory in the flavor of Friedman, who did similar things for K3 surfaces. So we show that. So here, in the previous thing, we consider Fibonacci smoothing of these things. So we take some particular fiber of the smoothing, which is nice enough to glue. So we glue X0, the components of X0, we choose a gluing in such a way that X0 is semi-stable, which means there's a nice log smooth structure. And then we do log smooth deformation theory to show that we can smooth X0 in a way that the total space is smooth, X0 lives inside the normal crossing divisor, and then separate results, we prove the total space is quasi-projective with trivial canonical bundle. And furthermore, there exists a contraction from the total space to X bar. Such that this the X bar is affine with canonical singularities, and this contraction is a projective Crepont resolution. So the idea is to show everything on the level of X0 and then lift to the total space. It uses quite some log smooth deformation theory. Friedman earlier showed how to smooth K3 surfaces in a similar way. It's significantly different because we don't have compacts, or X0 has non-compact components. The other differences, it's a very beautiful proof using -1 theorem for K3 surfaces, saying if you're in the degeneration of K3 surfaces, everything component is a union of cycle of -1 curves. That's the main starting point. Here we don't have that. So we prove this using some deformation theory. And then we study the birational geometry of the smoothing. So there's a minimal model program which has generalizations to various setups, to the analytic setup. There's a formal minimal model program. So we use in the formal setup that this Crepont resolution results of the minimal model program show that this is a Mori dream space. Hence, there's a complete fan, the Mori fan, living inside the relative Picard group whose maximal cones are the unions of all possible Neff cones of all possible Crepont resolutions of X bar together with the additional bogus cones. And then, similarly as before, we want to define our KSB moduli space to be the fan associated to this Mori fan of this mirror. So we want to define the secondary fan as the Mori fan of this mirror. We don't quite do that. We define a coarsening of the Mori fan, which was the idea of taking the coarsening was suggested in the paper of Hacking Hülya. We just identify some neighboring cones. If two neighboring cones in the Mori fan differ by an N1 plot, which means if you have an exceptional curve here, if the birational morphism you have just contracts that and flows up on the other side, this is an M1 flop. And then we identify two cones. We define this coarsening of the Mori fan, and we declare it to be the secondary fan, which is a generalization of the secondary fan for toric varieties in the non-toric setup. of this quotient Morifan. And we will show our KSP modular space is a family over this time. Okay. So our goal then, once we have this half of the story, once we construct a mirror, our next goal is to show that the toric variety defined by the secondary fan is a finite cover of the KSP modular space. Just to make sure, how much time do I have left? Oh, great. Okay, thank you. I have 5 more slides. So our goal is to show that the toric variety defined by the secondary fan is a finite cover of the KSP modular space. And to show this, the strategy will be to construct a family of stable pairs over the toric variety corresponding to the secondary fan. By the universal property, this will give a map from the KSP modular space to the toric variety. And we will show this is projective and finite. And to show this, at this point, we will take the mirror of the mirror we construct. Now we can do the intrinsic mirror of what we construct of Gros-Seibert. Maybe let me mention that in the known examples that were given in the 6 situations where you have your mirror just ky to y, here and you use the non-Archimedean mirror construction, and well, I'm not really an expert, at least yet, at all. Yes, it should be unset to this modular space. Yeah, sorry, thank you. And yeah, so we will construct this KSP modular space over M6 by intrinsic mirror symmetry. In the 6 examples now, here you use non-Archimedean mirror construction, but at least I'm not aware if there is a version of the non-Archimedean mirror construction of a field with non-trivial variation. We will have things of a formal, spec formal, and so on, which I wouldn't know how to do.
So this is the same to say that we have this stack which you figure all this here instead of saying the
we will show we have a finite cover. It's possible we might be able to say more if we analyze the geometry of the finite cover. Like, I don't know if it would be a lot stronger, I think, if we know the normalization of the KSP modular space is a toric variety, like in Battery's case. I think we haven't really investigated on this so much. So far, we only know it's a finite cover, but we might investigate on this. Yeah. Okay, so to run the Gros-Seibert intrinsic mirror symmetry, so here it's just the upshot of intrinsic mirror symmetry. When you have a projective family of Calabi-Yau, Gros-Seibert provides an intrinsic mirror symmetry construction, which constructs a mirror family of a spec formal of C double brackets and EX. And this construction uses punctured low chromovit interior of Abramovich Gros-Seibert Chen, which give the structure constants. So your mirror family is going to be given by an algebra of theta functions. The structure constants will be punctured invariants. We cannot actually directly run the Gros-Seibert mirror construction. It's a generalization of it in some way. The problem is, so far Gros-Seibert worked only for projective, in the projective setup. Our family is only quasi-projective, but we do show that actually, although our family is just quasi-projective, we have this map from X to X bar, which with projective fibers, and we do show all of the punctured low chromovitin invariants that appear in the mirror construction live in compact spaces. The modular spaces are all compact, so we can generalize the Gros-Seibert into this setup. And one of the key theorems we prove is actually, we still call it the intrinsic mirror, the intrinsic mirror actually extends from this formal spec formal thing to the affine toric variety, spec C and X, whose form is the left-com of X. So this uses quite some involved analysis of showing if you have two theta functions generating the mirror, their product is defined by a structure constant given by punctured log curves. And we showed there are only finitely many possibilities for this punctured log curve. So we use some birational geometry of the Crepant resolution to constrain the curve classes that appear in the mirror construction to prove this. So this is one of the key results. And then, sorry. So at the end of the day, we obtained the intrinsic mirror with this affine toric mirrority. But we don't want only, we want to construct a KSP family. So we don't only want this Y, the mirror, which will be a family of Ys, but we also show we can find an ideal by, so the mirror will be a ring of projective variety generated by theta functions. We define an ideal corresponding to the interior points of the polytope given by the cone of our Symington polytope. We obtain a divisor this way. And then we also define the third data. We need the curves, family of curves, Cx, by looking at this natural line model O1 and then define this divisor this way. So the next theorem we show is that this family with this divisor, with these curves in the total space, is a family of KSP stable surfaces over this affine toric variety. And furthermore, the general fiber is the formation equivalent to our original YDL. The first part of this, the first theorem is the first part we show. It's used with birational geometry interpretation again of the faces of the net cones to analyze the mirrors and obtain an inductive description of the mirrors. The second part uses, some part of it uses my old work to analyze up to diffeomorphism, the general fiber of Gros-Seibert mirrors to identify with YDL. And then some result of Friedman shows if you have diffeomorphic YDLs, you can obtain, you can apply some results of Friedman to show deformation equivalence. Okay. So the final thing is to show once you obtain all these mirror families over the affine toric varieties, for different Crepant resolutions, we show you obtain different mirrors, different KSPA families, but you can glue them together over the secondary family. And the proof of this is should be included in some way of what Grosek and Seibert announced in their ongoing work in progress. It uses some similar gluing arguments. We can glue the mirror family. So the final thing is, once you glue all these mirrors, we show you obtain map from your toric variety to the KSP moduli space. I'm writing this in the right order, right? Sorry. Such that it is finite and surjective. And to show finiteness, we show there's this idea that's already appeared in the paper of Hacking Hülya that over on the base of a one-dimensional strata, the family is not constant, which has to do with the identifications we do if we have N1 flops. And this shows like injectivity roughly, and then we calculate the dimensions and to show surjectivity, so we get this finite cover. And thank you for your attention. This was it.